Hello everyone, this is a series on relation and function of class 12 and today we'll take up the topic relation. Before we go to the topic of relation, let's first understand the Cartesian product of two sets. So we are going to take set, say 1, 2, 3 is set A and set B is 4, 5. So when we are finding Cartesian product, that is A cross B, we will pair the elements of A with the elements of B. So that's 1, 4, 1, 5, 2, 4, 2, 5. As you notice, the first element is from the set A and the second element is from the set B. Now, this set A cross B has n of A into n of B elements, number of elements in A cross B. That means there are 3 elements here and in B there are 2 elements. So total number of elements in the Cartesian product of A and B, that is A cross B, will be 6. As you can see here, there are 6 elements. And this 6 elements will have number of subsets as 2 raised to 6, that is 64. And all of the subsets are relations. So let's consider a few of the subsets. Like one of the subset is null set. Every set has null set as its subset. And then we have singleton sets like this ordered pair 1, 4. Ordered pair means first element is from the first set and second element is from the second set. Then we may take 2 elements. You will have singletons elements like this, so many, like 1, 4, 1, 5 is another set, 2, 4 is another set, but we are listing only a few. So you have like this, then you have 2 elements, then 3, 4, and finally you will have A cross B with 6 elements. So this one is known as empty or null relation because it has no elements. Whereas A cross B has all the elements, so it is known as universal relation. And as we said, we have 64 such relations. So the general formula for finding the number of relations is 2 raised to n of A into n of B. Now the ordered pair or the Cartesian product A cross B is not equal to B cross A, but the number of elements will remain the same. Like if you go back to the question, n of A cross B is 6 because it is n of A into n of B, and n of B cross A will also be equal to 6 because that is n of B, number of elements in B into the number of elements in A, so that is 6. Of course, the elements will differ, like in B cross A we will have 4, 1, 4, 2, 4, 3, 5, 1, 5, 2, 5, 3, like that. So the order of the elements here will change, but the number of elements will remain same. So number of relations will also remain same. Of course, the relations will not be equal. Now that is about when we take 2 different sets. Now suppose if we take a set, say A, and define a relation on this. So it should be any subset of A cross A. Let's first write down A cross A. Now one of the subset will be null set, another will be say 1, 1, and then we'll have another singleton set 2, 2. Like this we'll have all singleton sets. Now this set has 4 elements, A cross A. So the number of subsets or the number of relations will be 2 raised to 4, that is 16. So we are interested in particular relations where we have 1, 1 and 2, 2. Say we will write it as R1. That is 1, 1, 2, 2. This is a subset of A cross A. Right? You may write another. You put as many extra elements you want, but 1, 1 and 2, 2 are present in the relation. Then that relation is known as reflexive relation. Like reflection, reflexive. If 1 is there, 1, 1 should be there. If 2 is there, 2, 2 should be there. So talking about reflexive relations, if I have a set A which is 1, 2, 3, then any subset of A cross A which has 1, 1, 2, 2 and 3, 3. You may have elements more than this, or you may have only this many elements. This is a reflexive relation. So if the set was A equal to A comma B, then relation R should be AA and BB. Again, as we said, you can have more than that elements, fine, as many, but this element should be there. So that is a reflexive relation. In general, a reflexive relation is a relation where if A belongs to capital A, then A comma A belongs to R. Like we saw earlier, if 1 belongs to A, then 1, 1 should be there. If 2 belongs to A, then 2, 2 should be there in the relation. Every element should be related to itself. That's a reflexive relation. Now, taking the same example, that is set A, which was 1, 2. If I have a relation R, let's first write A cross A. Okay, so A cross A is 1, 1. So if we have 1, 2 in the relation, then we should have the reverse elements 2, 1 also. That is known as symmetric relation. So relation R, which is defined as 1, 1 is symmetric because the reverse of 1, 1 is also 1, 1. So that's a symmetric relation. So whichever element is there, if you flip the elements, then the element should be in R. That ordered pair should be in R. That is known as a symmetric relation. So if we take another example, like say, if you have a set A which is ABC, and we are discussing about R which is A comma B, then we should have B comma A. It would become symmetric. If we have AC, then we should have C comma A also. That is symmetric. So every element which is present in R should have a reverse element along with it, then it becomes symmetric. So in general, we write that a symmetric relation is one where if A comma B belongs to R, then B comma A belongs to R. So in case we have a relation R which is defined on a set A, 1, 2, 3 we will take. So if I have 1, 2 in this and 2, 3 here, then in order to make it symmetric, we should write 2, 1, the reverse of this, and 3, 2, the reverse of the other one, to make it a symmetric relation. So this is only symmetric. But if I have a relation R which has 1, 1, 2, 2, 3, 3, and I have 1, 2, and also 2, 1. So this relation is symmetric because 1, 1 reverse is 1, 1. So for this is a kind of ordered pair which will always be symmetric with the same elements. So we'll just look for where we have different numbers like 1, 2, its reverse 2, 1 is there. So it becomes symmetric. Also according to the first one, that is reflexive. If 1 is there, 1, 1 we find here, 2, 2, 3, 3. So this relation R1, let's say, what we defined here is reflexive as well as symmetric. So relation may be more than one kind. Let's go to one more which we have here, that is transitive relation. Let us take set A as 1, 2, 3. And if we write down the Cartesian product of A with itself, we will have 3 3s are 9 elements. So let's list them. So in case if we take a relation R, which is say 1, 2, and we have 1, 1, and we have 2, 3, then we should look for n ordered pair which ends with, say like this one, it is ending with 2. Then which ordered pair begins with 2? 2, 3. So we should have another ordered pair with this element, that is 1, 3. If we have such a case, it is said to be a transitive relation. Let's define one more. Say relation R is 1, 2, 2, 3, and 3, 1. So in order to make it transitive, we should have 1, 2, 2, 3. So 1, 3, the first and the last element. That ordered pair should be there. Now you see here 2, 3, 3, 1. So we should also have 2, 1. Okay. Now any other? 3, 1 and 1, 2. If we write it, because in a set you can write it in any order. So 3, 1, 1, 2. So we should have 3, 2 also. So all possible pairs should be there. Also 3, 1, 1, 3. So we should have 3, 3. You have to check for every element. 3, 2, 2, 1. So we should have 3, 1. That's there. 3, 2 and 2, 3. See here. 3, 2 and 2, 3. So which element should be there? 3, 3. We have written that. Okay. Did we miss anything? Yeah. 2, 3 and 3, 2 is there. We can see here. So we should also have 2, 2. We have 1, 2 and 2, 1. So we should also have 1, 1. I think that is all. We have completed the whole set. Now we may not get more, we will not get more than these elements. So we can see that because in order to make it transitive, we have to look for every possible ordered pairs which end and begin with the same number. So that the final element like 1, 2, 2, 3, then 1, 3 should be there. So we kept on including ordered pairs so that it became transitive. In doing this, we came across a relation R, which is obviously transitive. But if you see, we do have 1, 1, 2, 2, 3, 3. This made it reflexive. Also, every ordered pair has a reverse element, like 3, 1 has 1, 3, 2, 1 has 1, 2, 2, 3 has 3, 2, and so it became symmetric also. So this is a relation which is reflexive, symmetric, and transitive. A relation which is all of the three, that is reflexive, symmetric, and transitive, is called equivalence relation. So we have reflexive relation, which we said is, if we are considering a relation on A, and if A belongs to capital A, then A comma A belongs to R. This is reflexive. So for every element, we should have its same element associated with it or related with it. That is known as reflexive. Symmetric. If an element belongs to the relation, if it is there in the relation, then its reverse element should also be there. That is reflexive. That is symmetric. Symmetric. Okay. And transitive is if AB and BC both belong to R, Then we need A comma C belonging to R. Okay. So let's consider one relation again. Say we have taken on the set A, which is 1, 2, 3. If I take R as 1, 1, 2, 2, and 3, 3. This is reflexive because every element is associated or related with itself. So it is reflexive. Yes. It is symmetric because 1, 1, you flip it up. Yes, it is there. 2, 2, 3, 3. It is symmetric. About transitivity, here we said, okay, if AB and BC both belong to R, then only we need AC. So if 1, 1, there is no ordered pair starting with 1. So yes, it is automatically transitive. This is the smallest relation possible on a given set, okay, where we write only the reflexive elements. It automatically becomes reflexive, symmetric, and transitive. It is also known as identity relation. It will have the same number of elements as the elements in the set A. Identity relation will have same number of elements as in set A. So on the same set A, if we consider a relation R which is 1, 2. Now this relation is not reflexive because we don't have 1, 1, 2, 2 and 3, 3. No, not reflexive. It is not symmetric because we have 1, 2, but we do not have 2, 1. But yes, it is transitive. Since for 1, 2, there is no element which is beginning with 2. So it automatically becomes transitive. So be careful with this thing, that if AB and BC both are there, then only we are interested in getting AC. Otherwise, it automatically becomes transitive. So this is the concept of reflexive, symmetric, transitive, and a function, a relation which is all three, that is reflexive, symmetric, and transitive, is called an equivalence relation. Now, sums based on this topic we will take up in the next video. So see you in the next video. Hit the bell icon to get the notification. Thank you.